Now we're going to talk about nuclear safety. This is for 1 billion kilowatts of electricity flowing for 1 year. The red items here are where electricity is generated by fire. And you can see that the fatalities for liquefied petroleum gas are 3.1, hydro is 0.9, and oil is about a half of that. Coal is about the same as oil, and wind is half that of coal. Natural gas is half that of wind, and nuclear is the lowest. You can see that nuclear energy is 100 times safer than hydro. And that's because there have been hydro dams in other parts of the world that have failed, and they've just drowned thousands and thousands of people. So that's why that number is so high. Now, all of the red ones here are powered by fire, and nuclear energy is the only source of energy that can replace all of those fire sources for generating electricity. Now, if we look at the numbers, hydro is 16%, coal is 40%, wind is 3%, natural gas 22%, and nuclear is 12%. Now, amazingly enough, coal is the largest source of generating electricity, and it's growing the fastest. It's growing the fastest when you look at the figures. Nuclear energy is also growing. As we talk, there are 70 new nuclear plants under construction in 15 countries. And as I said, nuclear is the only one that can replace all those fire ones. This is a very busy slide, but it's a very important slide because it talks about the natural background radiation in millisieverts per year. Millisieverts per year is a way of measuring the effect of nuclear energy radiation on the human body. But this natural background radiation shows that we're living surrounded by it. San Francisco in the US Gulf states, 0.8 to 1.2 millisieverts a year. That's the lowest there is on the scale. And that's above the level it is in Bay Durfee. I have a small Geiger counter, and I've checked out a few places, so it's about the same as that. If you were visiting the Grand Central Station in New York City, it would be about 5 millisieverts because the whole place is clad in granite, which has some radioactive materials in it. If you lived in Denver, you'd be exposed to 6 to 12 millisieverts a year every year. If you lived in Sweden, it's up to 18. France is up to 80, and Ramsar, Iran is up to 700 millisieverts a year. People live there. They're as healthy as you and I, and there's no problems with living in that amount of radiation. Now, this is the background radiation, 6 millisieverts a year when the accident occurred at Chernobyl. When the level got 1.6 millisieverts above background, they evacuated 200 to 300,000 people. Why? With people living in background radiations much higher than that, why did they do that? Fear and lack of knowledge, that's why. Today, we have evacuation levels of 20 millisieverts above background. And the big problem with evacuating at that level was not the radiation, but the fact that you moved all those people out of their houses for so long. They were depressed, there was suicide, that was really bad. And US nuclear workers are allowed up to 50 millisieverts a year. Every year that they work, they're allowed that. That's much higher than this. And if you just put those precautionary levels into perspective, Iran is up, Ramsar, Iran, up to 700 millisieverts. So these levels are very precautionary compared to that. Those levels we talked about were over a year. If you had 100 millisieverts in one day, that's a different ballgame. That's much more severe. And we were allowed up to 100 millisieverts a day at maximum. If you're in the position where you can save somebody's life and you get exposed to 250, well, that's okay. If you're exposed to 3,500 millisieverts a day and you get no medical attention, half the people will die. That's what LD50 means. 5,000 millisieverts a day and half the people will die with medical aid. That's very serious. That's the kind of radiation that killed the people at Chernobyl. Now just note that this is 35 times this. This is very precautionary. Remember this 100 millisievert number because we'll see it later when we talk about CAT scans. Now we're going to talk about microsieverts. These are 1,000 times less than the millisieverts we just talked about. Sleeping next to someone is 0.05 microsieverts. okay? We're radiating each other. Just sitting there, you're radiating people beside you. And if you lived 80 kilometers from a nuclear plant for 1 year, it would be 0.09 microsieverts a year. And if you ate one banana, it would be 0.1 microsieverts a year. Bananas have potassium-40 in them, which is radioactive. Now, if you if you live beside the Point Lepreau nuclear plant in New Brunswick, you'd be exposed to 1 microsievert a year, 1 microsievert a year. That's the equivalent of eating 10 bananas. So is there a problem there? Doesn't appear to be. And if you lived 80 kilometers from a coal plant for 1 year, that's 0.3 because coal contains radioactive materials like uranium. An extra day on the Colorado Plateau is 1.2 microsieverts a day. An airplane flight from New York to Los Angeles is 40 microsieverts, okay? Now we're going back to millisieverts again because we're getting into medical things here. If you had an X-ray, that's 0.14 millisieverts. That's lower than the background level. And so is a dental panoramic lower than the background level. Nothing to fear. A mammogram is 2 to 4 millisieverts, and that's about the same as an X-ray of your spine. Now we're going to talk about radio tracers. This is where they inject you with a liquid containing radioactive material that courses through your veins, and they take their readings. But now the most common material has a half-life of 6 hours. So after a whole day, the radiation level is 1/16 of what it was when it first started. So they need a high enough level to get proper readings, and then it decays very quickly so you don't get overexposed to radioactivity inside. Now, this material has such a short half-life, they have to keep making it all the time. So when the reactor at Chalk River broke down, there was a problem with medical isotopes because they have such a short life. You can't store them. You have to keep shipping them out every day and making new ones. A CT scan is 20 to 60 millisieverts, and a full body scan is 50 to 100 millisieverts. And that 100 is the maximum one-day dose that we saw earlier. But we readily expose ourselves to this sort of radiation level because this can tell us things about our body that there's no other way to find out. So these are very important to us. Now we're going to talk about nuclear waste and spent fuel. Nuclear is a very reliable way to generate electricity. And now we're going to talk about waste, and the waste is formed in the tube bundle inside this nuclear reactor. This is the boiler that generates the steam, which drives the turbine and drives the generator and sends electricity to our houses. So this is what we're going to see next, is a tube bundle. This is a tube bundle from a Russian VVER type of nuclear reactor. It's inside these tubes, they're filled with these pellets, which are about 1 centimeter in diameter, and they're sealed inside those tubes, and those are zirconium tubes. These tubes at the end are the control rods. When the control rods are in, nothing happens in here. But you pull the controls out, the radioactive material starts acting and generating heat and the things in action. Now, when all the uranium is used up, there is radioactive waste material that have been formed from the uranium. And this continues to react and generate heat. And it has a level of heat output about 3 to 5% of what the total output is with uranium. And so we can't leave it there because that's enough heat to melt the bundle. So that's immediately put into a swimming pool for a few years where the radioactive material decays and the heat level drops. When it drops to a low enough level, it's put into dry cask storage. Now, this is what dry cask storage looks like. These are steel cylinders wrapped in a little bit of concrete, and inside theirs are the tube bundles. Sealed inside each tube bundle, there's a little bit of very long-lived radioactive material. Lives half-life of 10,000 years. But there's so little of it that even a little bit of steel can stop it, so it's not dangerous. These people are walking around with no particular protection, although they're probably wearing radiation badges. So this is no, there's not much of a problem with storing it like this. After the dry cask storage, the cask will be moved to central long-term storage when that's built. The material will reprocess to recover uranium-238. When uranium is mined, it's got 0.7% U-235, which is the active material. The rest is uranium-238. That doesn't get used up very much. But that's good fuel for fast reactors, so we have to recover that so we can use that. And then we can isolate the long-lived isotopes too. And for low-level waste like clothing and construction materials, we can incinerate those to reduce the volume and put the containers in concrete storage. We can, with low-level waste, which is clothing and construction materials, we can incinerate those to reduce the volume and put all that in robust concrete containers for long-term storage.